have discussed the branch currents and branch voltage. Here we have expressed the branch currents in terms of branch voltage. Yes or no? We express the branch currents in terms of branch voltage. Yes or no? So now let us obtain the equations by applying Kirchhoff's voltage law in each closed path. Okay. So this is what the branch voltage you got here, and this is what the branch voltage you got. And what is the branch voltage here you get? Tell me. R3 into what? I1 minus I2. Yes or no, all of you? Okay. Now, look at this, KVL in the first loop. KVL in the first loop. Okay. Let us apply the Kirchhoff's voltage law in this particular loop. These are the branch voltages we got: I1 R1, I2 R2, and R3 into I1 minus I2. Once you know branch currents, you can find the branch voltage. Yes or no, all of you? The polarity is how you got based on the direction of current through it. Understand, all of you? Okay. Now look at this KVL in loop 1. If you apply KVL in loop 1, what do you get here? Minus R1 I1 minus R3 into I1 minus I2 plus E1, yes or no, is equal to 0. This is first equation. Now if you assume that I1 greater than I2, then you get actually here I1 minus I2, yes or no? With this you got plus minus polarities, and you are moving in this direction. You are moving from higher potential, lower potential, fallen voltage. Fallen voltage according to us is negative. According to me especially, I am taking always fallen voltage negative, rising voltage positive. That's why I got minus. Now, or there is one line you leave it, okay? I'll tell you, there is a method called inspection. How we write using inspection also. Now, KVL in loop 2. KVL in loop 2. If you apply KVL in this, minus R2 I2 minus R3 into, now I am taking I2 minus I1 because if I assume that I2 greater than I1, look at this, all of you, what I am getting here, this is R3, I2 greater than I1 is what? I2 minus I1, upward direction. What are the polarities? Plus minus. You are moving again from higher potential to lower potential. Okay, this is what the direction, right? Again, you are moving higher potential to lower potential. Higher to lower, fallen voltage. Fallen voltage becomes negative. You understand? That is why in the first loop, if you write the KVL, you assume I1 is greater than any other loop current. In second loop, you are writing the KVL, then you assume that second loop current is greater than other loop currents. If you write like that, what is the advantage you get? You get negative sign before the voltage across each resistor. Simply you get negative, minus, 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 like that you can proceed. Okay? Well, now what about this? You are, okay, writing minus E2 is equal to 0. Second equation. Minus R2 I2 minus E2 minus R3 into I2 minus I1. Okay, I have given clear explanation here and leave one space for writing the inspection. Understand, all of you? Okay. See, first case I am just explaining elaborately, keeping in mind all different varieties of students. Okay, and this will just remove the confusion how we are writing the KVL equations. And later on, I can't explain, and I can't really spend this much time to elaborate it. Okay, please try to understand it. Okay. Now, don't write. Look at this. I'll give you sufficient time to write down the points. Look at this, all of you. So what is the step-by-step approach we followed? First, we have represented loop currents. Then we found branch currents in terms of the loop current. See, this branch current is what? Same as loop current. Why the branch current is same as loop current? Because this element belongs to only first loop. Okay. Here, branch current is same as loop current because this element belongs to only second loop. Okay. What is the branch current? Branch current is a resultant of what? Both the loop currents, because this element belongs to both first loop as well as second loop. Understand all of you? Okay, it all depends on the representation of loop currents only. Okay, now you calculated the branch voltage based on the directions of the current, you indicated the polarities, and branch voltage also you determined. Okay, now let us apply the inspection method after writing these equations. Okay, inspection. In the first loop, when you write the equation, you put minus I1. Okay, you're writing the equation in the first loop, then you put minus 1. You can ask me, sir, what is that minus? So the minus sign is a predefined sign. You don't like that minus sign, you can put plus also, doesn't matter. But I'm just starting with a minus sign for my convenience. Okay. Now minus I1 into sum of the resistors in the first loop. Please remember all these rules, all the statements clearly. In the first loop, sum of the resistors you can take R1 plus R3. Understand? Okay. Now I2. Listen to me carefully. Don't write. I2. Common element between first and second loop. What is that? R3. Okay. Now you must decide the sign of it. What is the sign of that? Sign we need to place before this I2 R3 component. For that, what you do is you check how the elements are flowing, how the loop currents are flowing in the element R3, common element. This is a common element, right? How the loop currents are flowing? One is downward, the other is upward. Don't say both are clockwise, not like that. In the common element, how they are flowing? One is upward, the other is downward. That means opposite direction. When the loop currents are flowing in the opposite direction, okay, you take the opposite sign to the predefined sign. Suppose you have minus, therefore it becomes plus. If somebody takes here, I wanted to go for plus, I start with, no problem. If you start with plus, it will become minus. Understand all of you? Okay. Well, but I generally take predefined sign minus, then I place plus with respect to, okay, the predefined sign, because both the loop currents are flowing in the opposite direction. Now, are there any energy sources in the first loop, particularly voltage sources? Yes, there are. How the loop current is touching the polarity? Negative sign first, therefore minus first, therefore minus. Minus E1. That's it. Negative sign first, therefore it is minus E1. Understand all of you? Okay. Now, second loop current. I think second equation you can easily find now looking at this. What is this? A predefined sign you want to place minus I2, because you are applying KVL in the second loop, you can take minus I2. Sum of the resistors in the second loop, Nana. What is that? R2 plus R3. And this is I1. Okay. Common element between the first and second loop. What is that? R3. How the loop currents are flowing in the common element? Are they flowing in the same direction or opposite direction in the common element? Opposite. Opposite to this, what is this? Plus is equal to how the loop currents are touching in the, okay, to the voltage source given in the second loop. It is touching positive sign first, therefore plus E2, second equation. You understand? Now you can write these equations directly in the matrix form. Look at this, all of you. Don't write. Just look at this. I'll give you time. How many variables are there? 2 variables. Now don't look at that. I'll tell you inspection directly here itself. Don't look at that. Now look at this. From the circuit, let us fill this entire matrix. How many equations you get? 2 equations. What is the size of the matrix? 2 by 2 matrix. Therefore, let me take 2 by 2 matrix here. Okay, this is a 2 by 2 matrix. What is 1 1 element? What is 1 2 element? What is 2 1 element? What is 2 2 element? We have to fill them. 1 1 element is nothing but minus of sum of resistors in the first loop. What is 2 2 element? Minus of sum of resistors in the second loop. What is the common element between the first and second loop? That is R3. Okay. R3. But how the loop currents are flowing in the common element? Opposite direction or same direction? Opposite direction. Take the opposite sign to this. Plus. 1 2 element is same as 2 1 element. This is now plus R3. Okay. Remember, this element there is no need to find. 1 2 element is same as 2 1 element. Why I stated that? Because this entire matrix will satisfy off diagonal symmetry property. Understand all of you? What is off diagonal symmetry? Ith row jth column element is same as jth row ith column element. That is nothing but off-diagonal symmetry property. Remember, in the node analysis, mesh analysis, wherever you go, when you write the equations, definitely that matrix will satisfy off-diagonal symmetry. Okay? Therefore, for this element, there is no need to look at the network. You can directly take this element as it is and copy paste. What is this? I1 and I2 is equal to energy sources touching negative sign first minus E1, touching positive sign first plus E2. That's it. So once you know this, I1 is equal to delta 1 by delta, I2 is equal to delta 2 by delta. You know how to apply Cramer's rule, and you can solve for this and this, you can get the answers. Understand, all of you? Now onwards, we must be in a position to draw directly the matrix form looking at this network using a method called inspection. Okay, this is called inspection method. This inspection method will help you a lot even in the control systems. Okay, inspection method, even in the control system, it will help you a lot to determine the transfer function of a mechanical system or electrical system or electromechanical system. You have some force voltage analogy, force current analogy, torque voltage analogy, torque current analogy. Okay, different analogies are there. Okay, so simply you can find the transfer function within one step. You can draw that matrix form first, and then one step use the Cramer's rule to get the transfer function. Okay, so please note down all these things clearly. It is the first example that is negative. It is a predefined sign. But off-diagonal element, 1, 2 element, 2, 1 element, this sign depends on how the loop currents are flowing in the common element. Are they flowing in the same direction? Then you will have a same sign. Opposite direction, opposite sign. In this context, one is downward, the other is upward. So opposite to this negative sign, I have taken that is plus sign. Okay. We will see different cases. Just from the network, immediately you can recognize how many minimum number of loops or minimum number of equations required. Okay. We always look for minimum number of equations. So let me select this is clockwise and this is anti-clockwise. Then we will see what will happen. Okay. So I guess all of you finished this. Let me erase. Now for this problem, let us write the equation. Let us write the equations for this problem. First loop, KVL in loop 1. First loop, what are the elements? Minus R1, I1, minus R3, but loop currents are flowing in the same direction. I1 downward, I2 is also downward. First we write normal equations, then we go for inspection. Okay, R3 into loop currents are flowing in the same direction, therefore I1 plus I2, then plus E1 is equal to 0. Equation 1. Leave one line space for inspection. KVL in second loop, okay, KVL in second loop, you can again take minus R2, I2, minus R3, again here, same I1 plus I2, yes or no? Then plus E2, you are taking rise in voltage, fall in voltage concept here, then R, right? Now inspection says you take minus I1, first loop current predefined sign minus sign. Sum of resistors in the first loop, what are they? R1 plus R3. And then I2. Common element please, R3. How the loop currents are flowing in the common element? One is downward, the other is also downward, both are downward, both are flowing in the same direction. Same sign as the predefined sign minus. And how this loop current is touching the polarity of the source? Negative. Therefore, minus E1, equation 1. Similarly, minus I2, R2 plus R3. Now, I1 of R3, but minus why? Because loop currents are flowing the same direction, is equal to touching negative sign first, minus E2. That's it. So I told you directly, let us not write all these things in future. It is only for just getting clarity. Once again, I'm writing, but you don't need to write all these things. Directly go with the inspection. 2 by 2 matrix. Tell me, look at the network and tell me, minus of R1 plus R3, minus of R2 plus R3. This is a 2 element, right? Then what is the common element? R3. Therefore, plus R3 or minus R3? Minus R3. Why? Because in the common element, the loop currents are flowing the same direction, same sign. And first row, second column and second row, first column is same. Why? Because there is an off-diagonal symmetry. We have mentioned already here, always it satisfies off-diagonal symmetry. What do you mean by off-diagonal symmetry? Ith row, jth column element is same as jth row, ith column element. Okay, that's what we have seen. First row, second column is same as second row, first column. Into I1 and I2 is equal to touching negative sign first. Here we are applying negative touching concept. Okay, touching concept, minus E1 minus I2. That's it. So I1 is equal to, okay, you can go with now from this simply delta 1 by delta, and I2 is equal to delta 2 by delta. Note down, please. You also note down here off diagonal symmetry, Aij is equal to Aji in the previous case. Remember always the matrix. Third case. So what is third case? Actually, I'm taking here I1, I2. I'm taking now the first and third loop. Okay, 1, 3 I'm selecting. Let us see what will happen, how we write it. Because in the exam, sometimes the loop selection, the loop current selection might be already defined. Okay, already defined and given to you. Then what will you do? You are supposed to write the equations based on the loop currents given. Now, KVL in the first loop. Look at this. What is the current flowing through this element? What is the current flowing through this element? And what is the current flowing through this element? It all depends on what the representation of loop currents. So the first loop, what are the elements belong to? What are the elements belong to first loop? Look at this, what I1 is doing, passing through R1, R3, E1. What are the elements belong to second loop? R1, R2, E2, E1. I ask you the question in a different way that, what are the elements belong to only first loop? Only first loop means what? See, look at this, R3 only. Yes or no? R3 only. What are the elements belong to only second loop? R2 and E2. Because you look at this, I1 is passing through R1, R3, E1. I2 is passing through R1, R2, E2, E1. That means E1 and R1 are becoming common elements for these two loop currents. Yes or no? Agree all of you? Therefore, the element which belongs to only first loop is R3. Therefore, its branch current is same as loop current. If you connect an ammeter in series with R3, it reads only I1. If you want to get I2, then where do you place ammeter? You place in series with R2. If you place in series with R1, how much that ammeter reads? Tell me. It reads I1 plus I2 because I1 is flowing in this direction. I2 is flowing in this direction. Yes or no, all of you, okay? So this current is I2 and this current is what? I1 plus I2. Branch currents are expressed in terms of loop currents. Okay. Now KVL in loop 1. What are they now? How do you write? Minus R1 of I1 plus I2 minus R3 I1 plus E1 is equal to 0. This is the first equation. And we write that inspection directly in the matrix form. Okay. KVL in loop 2. Tell me. Minus R1 of I1 plus I2 minus R2 of I2 minus E2 plus E1 is equal to 0. Yes or no, all of you? Minus R1 I1 plus I2 minus R2 I2 minus E2 because fall in voltage and then rise in voltage. That's it. You got two equations. Now let us write the matrix form directly. Inspection. 2 by 2 matrix, right? 1 1. What is 1 1? The elements belong to first loop. Resistors R1 and R3. Negative sign. What is negative? Predefined sign. R1 plus R3. Negative. 2 to element. Elements belong to second loop. What are they? R1, R2. R1 plus R2. What is the common element? The common element is what? R3 or R2 or R1? R1 is the common element. Yes or no? Yes, R1. How the loop currents are flowing in the common element? Same direction. Same as the predefined sign. Minus. And for this element I told you already, there is no need to put efforts, directly copy paste because off diagonal symmetry is there. Okay. I1, I2 is equal to touching negative sign first minus E1. Touching positive sign and then negative sign I2, I'm talking about. There are two voltage sources present in the second loop representation. Okay. First loop representation, you have only one source. Therefore, plus E2 minus E1. Then you can apply Cramer's rule to find I1 and I2 values. That's it. Please note down. This is the third case. Note down that here. This is case 3, right? Not case 2, okay? Please correct it, okay? This is case 3 actually. Now example. Example. Same networks I'm taking here. All of you note down first. All of you note down. This is R1, R2, R3, E1, E2, E1, E2, again R1, R2, R3. Now here the current flowing is I1. Here the current flowing is I2. Current flowing is I1 dash. This is I2 dash. Okay. Then please note down, if I1 is equal to 10 amperes, I2 is equal to 3 amperes. Okay. Then I1 dash and I2 dash values are. Okay. What are the values of I1 dash and I2 dash? Note down that all of you, the question, simple question, example. Note down that. Okay. So the networks are same, only the representation of the loop currents are different. Yes or no? The networks are same, but the representation of loop currents are different. Then what does it mean? How do you really solve it? What is the concept actually here? Okay, loop currents are different, but branch currents remain same. Yes or no? Okay, loop currents are different, but branch currents remain same. Yes or no? Now what we do is, we find the branch current in R1 here and R1 there. We make it equal. We find the branch current R2 here, R2 there. We make it equal because already the data is given here I1 and I2 values. We can find based on that I1 dash and I2 dash easily. Yes or no? Or else you can find even current through R3 also here, R3 there. Anything is okay, but the concept is very simple. Branch currents remain same, although loop currents are different. Okay, so write down the point here. Branch currents remains the same, although loop currents are different. Loop currents are different. Okay. Now you can see here. What is the branch current here? This is I1 plus I2. What is the branch current here? This is only I2. Yes or no? Because this belongs to both first loop and second loop according to this representation. This belongs to only second loop according to this representation. Now here the branch current is what I1 dash. Here what is the branch current? I2 dash. Okay, I2 dash. Now tell me. Here, okay, I1 dash will be same as what? I1 plus I2. I2 dash is equal to minus I2. That's it. So what is minus I2? Why? Because see the I2 dash is flowing in opposite direction in R2 to I2. Therefore, I can put minus in here. What is I1 plus I2? 10 plus 3. This is, okay, this is 13 ampere. What about this? I1 dash is equal to I1 plus I2. I1 is how much? 10 amperes. I2 is how much? 3 ampere. Now here I2 dash is equal to minus I2. What is minus I2 actually here? This is minus 3 ampere. I hope you understand the point. Okay. Like this sometimes the question may be asked. Okay. With the different loop currents selection, you may get the questions even. Note on that. Although loop currents are different, but the branch currents remain the same. Note on this. Meanwhile, I just case 4. I just write down here case 4. Let us investigate different cases. Note on this. I think all of you noted on that. Now note on this. Now if there is a current source, how we do it? Okay. If there is a current source, how we do it? Let's see. Look at this, all of you, in the case of current source. If you write the equation here, the loop currents, if I select I1 and I2, something like this, let us see what will happen. Suppose if you write the loop current here, plus E1, sorry, loop equation, okay, KVL, we are applying KVL in the loop 1. What do you get here? Plus E1 minus R1 I1. Now what about this? Do you have any voltage across this current source? Do you have any idea about it? No. So the first option is that you can assume some voltage is present Vx, some voltage, and take that equation and proceed. But what is happening with that? I1, I2 plus Vx is another variable is coming to picture. So more number of variables are coming to picture. So this is not really advisable. But that is definitely a solution, no doubt. Okay, one of the solutions. But that is not recommended because you are increasing the number of equations. What is our objective here? We want to decrease the number of equations. Yes or no? So that is not recommended. But you can go for a method called super mesh analysis. Okay? Super mesh analysis to deal with the problem. Okay, first we discuss what is super mesh analysis, then we see whether super mesh analysis is really good in the competitive exams or not, that we discuss later. Okay, first let us discuss super mesh analysis. According to super mesh analysis, step 1, please write down. Please write down. Express the loop currents in terms of current source value. Now tell me, how do you express? Because all these values are known values, including current source. We do not know only I1, I2 values. Yes or no? So I1 is downward, I2 is upward. So what is the resultant current? Either I1 minus I2 or I2 minus I1. I1 minus I2 is downward, I2 minus I1 is upward. Therefore, I2 minus I1 can be taken as capital I. Equation 1. How many equations you require to solve this network? 2 equations, because there are 2 unknowns. First equation you have got it. Now the second equation is obtained something like this. Step 2. First you write all this, please. Express the loop currents in terms of current source value. I2 minus I1 is equal to I. This is the first equation. Then second step. Suppress the current source or deactivate the current source. Suppress the current source or deactivate the current source. What do you mean by suppressing the current source? Nothing but what? Replace by its internal resistance. What do you mean by internal resistance here? What is the internal resistance of an ideal current source? Infinity, nothing but open circuit. Yes or no? Internal resistance is how much? For a current source, ideal condition, infinite. Yes or no? Therefore, suppress the current source, that means replace by its internal resistance, infinity. Then what will happen? As soon as this is suppressed, that is nothing but open circuit. Once it is opened, then loop 1, loop 2, mesh 1, mesh 2 both got merged. Yes or no? And these two meshes are merged and forming a common mesh. Yes or no? That mesh is called super mesh. Okay, therefore, which leads to the formation of super mesh. You understand, all of you? Which leads to the formation of super mesh. Understand, all of you? Now, let us also define what is a super mesh. Super mesh. Please write down that super mesh. First you write this, suppress the current source. Nothing but what? Replace by its internal resistance. What is the internal resistance? Infinity, nothing but open circuit, which leads to the formation of super mesh. What is a super mesh actually? It is simple, that merge of two individual meshes between which an ideal current source is connected. Please write down that. Merge of individual meshes. Merge of individual meshes between which an ideal current source is connected. Merge of two individual meshes between which an ideal current source is connected. Understand, all of you? Okay. So these are the two individual meshes between which an ideal current source is connected. Now it is forming a super mesh. It is something like this. Look at this, all of you. Now let me draw it. It is forming a super mesh. It is forming a super mesh. Okay. Now to get that equation, what we do is we apply KVL in the super mesh. Okay. We want ultimately what? Actually, second equation we want. There is one equation available here. We obtain this by expressing the loop currents in terms of the current source value. But we need another equation. That another equation is obtained by applying KVL in the super mesh. But when you apply KVL in the super mesh, we must maintain the previous branch voltages. Okay. So write down now here. Write down here. Now apply Write down, all of you. I think all of you noted down this, right? Now you can write. Now apply KVL in supermesh with previous branch voltages. With previous branch voltages. With previous branch voltages. What is the previous branch voltage here? Plus minus I1 R1, yes or no? Because what was the branch voltage here? I1 R1. Here I2 R2. Yes or no? Similarly, here also plus minus I2 R2. I1 R1, I2 R2. Yes or no? Now let us apply KVL in this. Minus R1 I1 minus R2 I2 minus E2 plus E1 is equal to 0. Understand all of you? Okay. You got two equations and two unknowns. You can solve them and you get the values. Okay. So please note down this quickly here. You got this. Now apply KVL in the supermesh with previous branch voltages. Important observation. Look at this, all of you. Don't write anything. Now I give important points. Okay. Look at this. Now suppose if I choose the loop current something like this, I1 and say this is I2. Say this I is equal to some 10 amperes, let us assume. Let us assume that I is equal to 10 amperes. Now see what is happening here. If current flowing in this loop is I1 and this element belongs to only first loop, if I express loop currents in terms of current source value, what I am getting I1 is equal to what? Simply minus 10 amperes. So from the network itself I am observing that the current flowing in this loop with this particular representation of the loop currents is what? Minus 10 amperes. Now what is the unknown value here? Only I2. That means only one unknown is left. Then how many equations required? Only one equation required. Then I am able to solve the same problem using what? One equation. If I go for supermesh analysis, I require two equations. But if I go for the representation of the loop currents carefully, if I choose, I am getting only one equation. That's a very important observation, that what are the minimum number of equations required to solve the network for this particular problem? Only one. What are the number of fundamental loops? Two. Fundamental loops 2, but number of equations required is only one. Just imagine, we gave a statement, okay? Minimum number of equations required to solve the network is what? As many number of as fundamental loops. But here that condition fails. Yes or no, all of you, okay? So therefore, put a note and write down. It's very, very important here, okay? It's very, very important. In a given network, write down. In a given network, the minimum number of equations in a given network, write down like this. In a given network, if it consists of L number of loops, then the minimum number of equations required is also L. Put a note and write down. In a given network, okay, if it consists of L number of loops, then the minimum number of equations required is also L. Full stop. But this condition fails when there are ideal current sources. Okay, when there are ideal current sources, what's happening here? Okay, minimum number of loops 2, but minimum number of equations required is 1. If you choose the loop currents in a different fashion. Yes or no? Okay, write down. In such cases, the number of equations depends on Okay, selection of loop currents. Selection of loop currents. Is it clear, all of you? Okay. So we'll stop the session here and we'll continue the discussion in the next session. Okay. It's very interesting discussion we are going to discuss. Okay. And how to count the number of loops, minimum number of loops for a given network. I stop the session here.